So what we can calculate after doing the algebra and applying our boundary conditions are two things that we call a transmission coefficient and a reflection coefficient. So we can calculate a transmission coefficient T, and we should think of T as the probability for tunneling through our barrier. And that turns out to go like, it's going to depend on sort of the amplitude of this transmitted wave to sort of our incident wave A. So it's going to be given by c squared over A modulus squared, kind of like a theme we've seen before. It turns out to be sort of the modulus square of an amplitude that gives us a physical probability. If you're curious about why this is, watch the bonus video from Friday's class. The argument for why it makes sense to define a transmission coefficient in this way comes from thinking about what's called a probability current. We can also similarly calculate a reflection coefficient, which is the probability for a particle to be reflected. And that, not too surprisingly, is going to go like the amplitude of this term, so this, our reflected wave, divided by our incident amplitude, A modulus squared. Now, it's not going to be super important for us to try to write down what the exact forms are, because they're kind of messy anyway. But there is sort of one sort of limiting case that is instructive. So, namely, if kappa A is much larger than 1, right? So if we have a sort of a wide barrier and the energy is low relative to V naught. If kappa A is much larger than 1, it turns out that the transmission coefficient has the following scaling. We're not even really going to care about the prefactor here, so I'm just going to write this as T is proportional to e to the minus 2 kappa A. Right? So what this tells us is that if I widen my barrier, right, I'm going to be exponentially more unlikely to tunnel through. And similarly, if I make my k larger by having a lower energy relative to V naught, I'm going to exponentially suppress my probability for tunneling. So I now want to do a clicker question to think physically about the result that you get when you actually apply those boundary conditions. Okay, so hopefully you've had the chance to think about this. Maybe you reasoned that the speed of the particles that made it through the barrier is equal to the speed of the particles that were incident. There are several ways you could think about this. One way is to recognize that on either side of the barrier, the potential energy is zero, so the energy is all kinetic energy. Remember that we're solving here for an energy eigenfunction, that is, a solution of the time-independent Schrodinger equation that has a definite energy. We're in an energy eigenfunction, so the energy is the same, right? It doesn't depend on position in any way. So if the total energy is the same on either side of the barrier, which it is, then since there's no potential energy, right, the kinetic energy has to be the same on either side, and we conclude that the particles are going just as fast on the far side of the barrier as when they were incident. Moreover, another way you could think about this is to recognize that what matters for determining the energy of the particles is their wave number k, or equivalently, their wavelength. And you can see from the graph that the wavelength of the oscillations is the same on either side of the barrier. So this is something that's quite different in quantum mechanics as compared to classical mechanics, right? Where classically you would not expect you wouldn't expect a particle to be able to penetrate a barrier in any case. You probably wouldn't expect it to be going with the same speed afterwards if it could. So there are one or two more things that I just want to talk about today. One of them is sort of a theme that we've maybe had come through a few times. Is this quantum tunneling some sort of spooky quantum phenomenon, or is it really a something that shouldn't be too surprising given how classical waves behave? My argument, as we've said several times, is that sort of quantum tunneling is really not magic. It's really more of a fundamental thing that waves can do. So there's actually a really cool demonstration of this you can do with light. And I'm going to link to a YouTube video that has a live demo of this. If we were together, I might try to see if I could do this as a demo. Unfortunately, I can't. But the setup is as follows. Imagine you have a glass prism like this, and the index of glass is larger than the surrounding air. If the index is high enough, what you can get is the following situation. That if I have a beam that shines down like this, right, that at this interface here, the beam gets totally internally reflected. So it'll just come out like this, sort of perfect reflection, no transmission through the interface here. So one thing that you probably didn't talk about when you study TIR in Physics 217 is that even though the wave is entirely reflected in TIR and though all the energy is carried by this outgoing ray here, it still happens to be the case that when you write down Maxwell's equations at a boundary in this kind of geometry, you get this exponentially decaying at what's called an evanescent wave out here. And so it decays exponentially, kind of like what we had with the wave function in the classically forbidden region, either in the analysis of scattering from a potential step or this kind of tunneling through a barrier. But even though this evanescent wave carries no energy, you can show, and so it's generally not of any consequence, and the main thing is really all the energy gets reflected. However, what you can do, and what they do in the demo, is if I have now another piece of glass, and they're using a curved piece of glass here, but the effect is still the same, and I'm failing at drawing this, but if you imagine sort of another piece of glass here, right, so that you have sort of glass again, and then in between this prism and that glass plate, you have a really thin air gap. It turns out you can actually have a little bit of the light that does sort of that evanescent wave that sort of tunnels through that air gap, and you get this sort of faint transmission through this interface that you wouldn't have in the absence of this other glass plate. So this is really a classical sort of analog to quantum tunneling, and the sort of mathematical analysis ends up being quite similar to what we did in the quantum mechanical case. But again, this goes to show you that tunneling is not
spooky or magic in any way, but it's a general property of wave behavior, one that you can see in some other contexts, including with light. So the last thing that I want to end with is an application of quantum tunneling, namely the scanning tunneling microscope and some of the fun things you can do with one. So we'll cut over to my computer to go look at that.
So here's a diagram of a scanning tunneling microscope. This is a device that's used to record images of atomic surfaces. The idea is the following. You have perhaps some electrons in your sample, and then you have this probe tip, and you apply a voltage to that tip. Now you keep an air gap between the tip and the sample, and because of this gap, there's effectively a potential energy barrier between the surface and the tip itself. So this is like what we talked about, except sort of now the one dimension we care about is vertical rather than horizontal. Because of tunneling, right, you can get a non-zero current through coming from the sample and up through your probe. And sort of the way these typically work is there's some sort of feedback system that maintains a fixed current by adjusting the gap between the sample and the tip as the tip is scanned over the sample. That allows you to get really high resolution atomic scale topographic images of surfaces. So we'll just close with two examples. So on the left you see an image of an STM image of individual gold atoms on a surface, right? And there you can see those little bright blobs. Those are individual gold atoms. And historically, the ability to see individual atoms and using STM was really was groundbreaking in physics. So on the right, I've put a link to a movie made by researchers at IBM, where they used an STM, the tip, to both push around atoms on a surface as well as to image them. So they made this cute stop motion movie that I encourage you to go check out the link. And so when we come back next time, what we'll do is we will begin to think about atoms, and we'll start by looking at the Bohr model of the atom, of the hydrogen atom. See you next time.